Now in part B, we're told that a particle of mass 5 kilograms is placed at A, so I'm going to mark in the weight, so that's going to act downwards at A, and that will be 5g newtons. And in order to maintain that this rod AB stays horizontal, the support, which was at C, that was down here, okay, has now been shifted to a new point, D. So where's D going to be? Well, I'm going to place D somewhere around here. Okay, we'll just mark in that support like so. Okay, and we'll call that point D. Now we've got to find that distance AD, so I'm going to call that X. Okay, X meters, and mark that in like so. Alright. And now that I've put that support in, we've got all these three forces acting downwards, and in order to stop that from moving downwards, we've got a force acting upwards from the support, the reaction on the support. So I'm going to mark that in. I'll mark that in there. It's not the same R as I used in part A, so I'm just going to put a subscript there, RD, the reaction from the support D, and mark that in as newtons. So I've marked in all the forces, and we've got to find then the distance A to D. And in order to do this, again, what I'm going to do is take moments now about D, because I don't want to get this force involved in the equation. So because it passes through the point that I'm going to take moments, it won't come into the equation. Okay, so we're going to take moments about D, so I'll mark that in here. I need to decide which way I'm going to have as positive. Again, it doesn't matter which way. So I'm going to take, in fact, turning anti-clockwise as positive. Why I'm going to take anti-clockwise positive is because I can see that if I turn in this direction, when it comes to looking at the moment of the 5g force about D, it's going to be 5g times plus x, and that just keeps the x positive. So taking moments then about D, it's going to be 5g, the force, times x, as I mentioned there. Then we have the 8g Newton force, so that's going to be 8g, and it's going to be turning in a clockwise direction about this point here. So that would be a minus 8g, the force, times the distance. That's this distance here. And what would that distance be? Well, we can see this is 0.75 and it's x up to here, so that's going to be 0.75 minus x. Then we have the 2g force, and so the moment about that would be 2g times that distance. And it would also want to turn in a clockwise sense about the point D, so that would be in the negative sense. So we would have minus 2g then multiplied by the distance dB. And what would that distance be? Well, we know the length of the whole rod was 1.5, so if the whole length was 1.5 and we subtract that x, that will give us the distance dB. So that's going to be 1.5 minus x. And because the rod is in equilibrium, there'll be no oval turning effect, so it'll equal 0. So all we need to do now is just simplify this. I notice that I can divide through by g because it's in each term, so we can divide through by g. That simplifies that part. So I've got 5x. Multiplying this out, we have 8 times 0.75, so that's going to be a minus 6, Then we have the minus 8 multiplied by minus x, that's plus 8x. And then minus 2 times 1.5, so that's minus 3. And finally plus 2x, and that equals 0. So gathering together the x's, 5x, 8x and 2x, that comes to 15x, so we therefore have 15x. Minus 6 and minus 3, that's minus 9, equals the 0. Add 9 to both sides, therefore we have 15x equals 9. And finally divide both sides by 15, and you have x equals 9/15. That simplifies to 0.6 meters. We're asked to find the length AD, which is x. So just to summarize, therefore AD equals 0.6 meters. And that brings us to the end then of part B.